have a question about one of these.
Yes, sir.
So I agree with her answer, but this part right here, so since those are the same value, go to 0, would you just do,
Yeah, do stuff like that.
you'd integrate it? So, okay. Is number 12 0?
No, number 12 is AJ's answer with a minus sign.
Oh, so it's negative L?
Yeah, negative. Which turns the log upside down.
Oh. Sorry, 15. And then
15, answer is 1/3
Here, I gotta do number
for
15.
15.
I did a terrible job in 15 then.
15 wasn't even the same problem.
What?
15 wasn't even the same problem.
So it was part of the time where I was like, I'm just going to do all the odds and check the answers in the back of the book to see if I can get one of them correct. I didn't get any of them correct.
Yeah, I was doing number 14 after putting on the board. I realized I had like completely wrong intervals.
Yes, I did too.
Did you say what you did wrong in here?
It should be minus.
Just a minus sign somewhere.
14 over 15.
Oh, no. Yeah, correct.
No, I know what I did wrong. Because this is supposed to have a minus sign right here.
These two are correct.
14's wrong. Because I didn't finish it. And 16, I'm not sure.
Okay.
Did you, what was the answer to 16?
Pi squared over 144.
Nope.
Alright. Sounds good.
I squared over 144.
It's just arithmetic at this point. Okay, we'll take a 10-minute break, then we'll resume with presentation and material. So we'll come back 7:30.
Would you be able to read the answers to 4 of the problems?
Sure I can.
Number 14.
Um, 14, better write it on the board because there's a bit to it. So the answer to 14 is 124.
That's weird. I haven't even shake this. It's been standing still and it just exploded.
Then 16.
Sure. Same, pi squared over 144.
Oh yeah, pi squared over 1.44 or 100?
No, 144.
32?
Hmm. 30.
36?
36?
I found 35 and 36 a little weird, because they want us to, cross multiply, or cross product those two, points, or?
Let me take a look at it. $32,
No, 35 and 36.
$35 and 36?
Yeah.
Oh, the technique of an average over a region. See the easiest way to say it.
I'm looking at 1 over AR.
I can do it in one dimension, it's easier. If you have a line that has the value 2 between x equals 1 and 4, and has a value of 4 between x equals 4 and 8, then what is the average value of y from 1 to 8? What's the average value of y from 1 to 8?
3.25?
Y 3.25.
Because 1 to 4 is 3 and...
Oh, that's right, so this is 5 and 9. Okay. So half the time it's equal to 2, and the other half the time it's equal to 4, agreed? So the average is that. So if you have a more strangely varying function than such as this, and this is y, and you want to know its average value over some length, you sum up all the y's from 0 to L, and you divide by the length to take the average value. So you add y at every point, and you divide by the number of points, true? That's L. So you do the same thing when you do it to 2 dimensions. If you have some base area, A, say it's a rectangle, and it's supporting some 3-dimensional surface, so it's supporting some 3-dimensional surface Z, agreed? Then what's the average value of Z over the whole area? Well, you take the value of Z at every point and you sum them up and you divide by the area, just as you did for 1 dimension. So if Z is some canopy that's sitting over this rectangle, and you want to know its average value as it's floating over this rectangle, then what you do is you take its value at all points on the canopy, and you sum them up, and you divide by the area under it. So this is the prescription for taking a 2-dimensional average. So is the picture fairly clear?
Well, I was asking about how in 35 you notice it says, I'm assuming our points, 0.01 cross 0 pi over 2.
Well, yeah, that's the, what in the world is that notation?
That's what I was trying to figure out when I was doing this problem, because I assumed it was a cross, so I typed it in as a cross, which gave me 0, which doesn't really give me much.
I would assume that's length cross width. So what we have is, 0, 3, or 0, what is the first one?
0, 1.
Doesn't matter, and 1, and then the other one is 0 pi over 2. So that this is your rectangle, length and width, length times
Oh.
width, length times width, right? Width times length,
So, okay,
that's what we want.
okay, because I was confused, because I was thinking it was like a cross product, which would only give me,
Yeah, that's quite possible, but I'm sure that's what the author has in mind here. He's just giving you the two sides of the rectangle. Okay, so the logic was clear to you anyway about how to take the average. Good. Okay, I'd like to now go to section 14.2. And this is going to be a fairly mental, painless extension of what you already know about double integrals and integration by iteration. Up until now, we have looked for volumes where we had some canopy in the sky that was over some rectangular region in the xy plane, so that our limits of integration on our double integral were just those of a rectangular region in the xy plane. So this was a double integral of like 2 to 4 and 1 to 7 of some function of x and y, which represents the height times dx dy. So these are the double integrals that we have used so far to find the volume of a three-dimensional solid that has a cross-section in the xy plane, which is a rectangle, and has some arbitrary function as its roof, some f of x, y, z as its roof. Now what we're going to do is relax that restriction, and of these four sides in the rectangle in the xy plane, we are going to allow two of them, opposite twos, to become functions, while the opposing twos remain as straight lines. So the picture to look at is in the book on page 1009. So in the two pictures on the left, you see this is what is called a type 1 region. Looking at the xy plane, which is going to be the footprint over which we integrate, then here we are keeping the x values at A and B to be straight lines, vertical lines, but we're allowing the other two boundaries to become actual functions of x. The top being a g of x, g2 of x, and the bottom a g1 of x. So when we do this integration, then we do it as in this example, 1. So in this case, the lower curve is y equals minus x. The upper curve is y equals x squared. So we perform the y integration between these two curves. So we take lengthwise strips. We perform the y integration between these two strips. We take vertical strips. So if this is our footprint in the xy plane, where we have two curves and straight lines, the first thing that we do is take an integration straight up between the two, from the lower value of y to the upper value of y. So this gives us the area in a vertical strip between y1 and y2. And y1 and y2 will now be functions of x. So y1 and y2 will be different as we now step through from left to right and add up the different strips. They're going to have a different height, because now their height is not uniform, but their height depends on the value of x for the vertical strip. So we now have the increased ability to calculate on footprints that now have two curves for opposing sides. And we can do it whether the two curves are x's or y's. So I'll attempt to draw one. If in the xy plane I have a curve y equals x squared, and then I have another curve y equals x cubed. Now, if I want to integrate between regions x equals 2, x equals 2, and x equals 3, then I'm going to be taking this part, x equals 2 is a line here, x equals 3 is a line here. So this is now my footprint in the xy plane. And if I have some canopy upstairs that has this as its footprint in the xy plane, then it has some volume under the canopy. And suppose that the height, z, some function of x and y, happens to be x and y. So it's going to increase up and out. Then the volume that's under the canopy that intersects the xy plane in this footprint, and let me draw this footprint in the xy plane so it's clear to us. If we have the curve y equals x squared, and then we have the curve y equals x cubed, then if we take the region from 2 to 3, then this is the footprint that is under that canopy. So our integral for the volume is going to be the integral of x and y, which is the height function of x, and we're going to integrate first in the y direction, and we're going to integrate from a lower limit of x squared to an upper limit of x cubed. So the integration in the y direction is going to be different depending on exactly where we are inside the footprint as we go from left to right. And once we do that, then the y's will be gone and we'll only have left a function of x. So we now close the integration with an integration over straight lines from 2 to 3. So let's do this partial integration. First, the x is a constant and y is evaluated. So the integral of y dy is y squared over 2. And that's evaluated from x squared to x cubed. And after that is done, then we have to integrate over dx from 2 to 3. So on the 1/2 comes out front. So we have the integral from 2 to 3. This x is right here. Now, on the top side, we're going to have x cubed squared. So it's going to be x to the 6th. On the bottom side, we're going to have x4 squared minus x4 dx. So just to complete the integration, it's going to be 1/2 the integral of x7 minus x5 dx from 2 to 3, which is equal to 1/2 x8 over 8 minus x6 over 6, evaluated between 3 and 2. And now I'm going to ask for a little help. What's the 8th power of 3? Sorry?
65, 61.
Over 8 minus the 6th power of 3.
$729.
Over 6, and that's going to be minus the 8th power of 2, which should be 256.
Yes.
256 over 8 minus the 6th power, which should be 64 over 6. So this is all times 1/2. So we've gotten it down to a little bit of arithmetic, and that's how you do these. Now you do it exactly the same way if your two curves are not y equals functions of x, but if your two curves are x equals function of y. So this is illustrated on page 1009 with example B, where first the x integration is done. And the width of the strip in the horizontal direction depends on where you are with y. So it turns out to be a function of y. So then you complete it by doing an integral over y between the two straight lines. So now let's have you actually do one. So page 1015. Can everybody do number 1? 1015, number 1. Have you actually do one. So you integrate over y, and when you finish the y integration, you insert.
Are we doing A or B? Oh, sorry, go check, disregard. Alright.
Problem number 1.
16 over 15. What do you get?
Negative 1/20.
Answer's 2/15. Is that what you got?
Nowhere close.
I got 1/20.
Okay, can everybody go up and do this in the whiteboard? Number 1. It's almost identical to the example I chose on the front board. So the steps will be the same. So AJ, did it end up at 2/15? Okay, your integration's fine. Okay, so he's got the arithmetic fixed now. Well, you didn't do it in 2 ways. You see, you know how to evaluate limits? Right? What's this sign?
Well, it would be minus -1, so it's going to be positive.
Oh, shoot.
Oh,
Scary.
Do it two ways?
Well, I don't know this technique, but if it's a valid technique, that's
Oh,
fine. Yeah.
I just plugged that in there, and then that's,
Okay. If it's a valid technique, that's fine. But, I've not seen it before.
it's 1/15 minus 1/24.
Yes.
It's 1/4, and then -1.
I'm not sure where the 1/4 appeared.
okay, that,
Oh, it's.
Oh, you mean you evaluated that?
Yes.
that makes
Okay.
more sense now.
Okay, good.
Sorry,
Okay.
140.
So everyone can now go to number 2, and the only difference with number 2 is that you're now integrating the x dimension first and the y dimension second. So this is to make you convinced that you can do either one first. One, and it becomes a function of the one you didn't do. Number.
16 or -16/15.
I got -1.
Thank you, AJ. AJ, you want to show them how to do it on the whiteboard?